All right, guys, welcome back to our continuing discussions about how light interacts with matter. Now, the last time we talked about the Beer-Lambert law, and we showed where that relationship comes from and why it is so incredibly useful, the incredible utility of that particular expression for doing things like measuring concentrations of things, right? It's just such an incredibly broadly useful and applicable relationship. But when you think about it, does the Beer-Lambert law explain in any way why a given piece of matter would absorb light? How it does that? And if you look back at that relationship, you realize, no, there's no mechanistic explanation there at all. It simply takes as a given that light will be absorbed and develops a rigorous mathematical relationship that can explain how much will be absorbed and that it's got to be related to some property of the material. But it doesn't say anything at all about why that happens, right? So fundamentally, that's an example of a quantitatively rigorous explanation that is non-mechanistic, right? It essentially gives you, it's a phenomenological description, however accurate that may be, that is basically just descriptive. There's no mechanistic insight. And to get that mechanistic insight into how and why matter of different kinds absorbs light of different kinds, you really have to turn back to a particular and specific and detailed formalism that was really only developed about a century ago. That is, of course, quantum mechanics. Now, we don't have time by a long shot to really dig deeply into the elegant, fascinating, and in many ways confusing ideas that fall out of the ideas of quantum mechanics. But there's still some key ideas here that are important for you guys as card-carrying biochemists or biophysicists to have a basic idea of, to really have a fundamental sort of basic grasp of. And we're going to focus the rest of this couple of lectures on this idea of how absorption works. So that's going to be our main focus here for the next, the rest of this lecture and the next lecture. How is it that the electronic structures of important molecules, biomolecules, in our case that we mostly care about, how is it and why do they absorb light? Okay, now these ideas, of course, will extend with elaboration to all kinds of other ways in which electromagnetic radiation interacts with light. But we're going to focus just on sort of the electronic absorption of light. Okay, now we're just going to be able to dip our toes in this idea, on some of these ideas. And because we don't have the time, and this really is not the right venue or the right course for a full derivation of many of these ideas, we're going to proceed from a set of postulates, right? We're going to take as a given that certain things have shown, about 6 postulates that we're going to assume have been shown rigorously, or sort of some of the foundational pillars of quantum mechanics. And then we're going to reason from those to illustrate this idea of absorption of light by matter. So we're sort of taking an approach that was kind of equivalent to what you guys may remember from your high school geometry, when you proceed from certain basic principles. All right, so our first postulate, I'm just going to call it postulate 1, right? Our first postulate is that the state of any system of n particles its state can be described as completely as possible by some function of really only 2 things, right? The position, or positional coordinates, of all the particles, right? Which is essentially be, that gets a symbol, this Q sub I, right? So in Cartesian space, the XYZ coordinates of every particle that constitutes the system, and time. Gets the symbol, of course, T. Okay. Now that function in the sort of abstract nomenclature of quantum mechanics also gets a symbol. And that symbol you may have seen before. It's a capital Greek psi symbol, right? And it is therefore a function of our system. It's this function would be a function of these positional coordinates, right? And time, right? And this gets a name, of course. This is known as a wave function. Right? Okay. So that is basically a postulate 1, right? Okay. Postulate 2. Whoops, that's the wrong tool. Okay. Okay, postulate 2. Postulate 2 states that the probability of finding that system, which we've described by this wave function, psi, the probability of finding that wave function in some differential volume, right, at some set of coordinates, right, some set of coordinates, right, and at some time, right, the probability of finding that system in that differential volume, which we're gonna give a symbol, this differential volume, d tau, right? The probability of finding the wave function in that differential volume in the universe, right, is simply this expression, which is that wave function d tau, right? Now I've done something a little funky there, right? I've added something, right? So that the probability here is related to that relationship, that product, right? Now, some of you guys may remember this, some of you may not, but that symbol there is not simply a multiplication, right? What we're doing, that symbol basically is related to the fact that wave functions are generally complex numbers. If you guys hopefully remember that complex numbers, right, have a real part and an imaginary part, the symbol I, right? So you have a complex number would be a plus ib, but complex numbers come in 2 forms, right? There's the number and then its complex conjugate, right, which would be a minus ib, and of course where I is equal to the square root of -1, right? That's sort of the definitional thing of complex numbers. This asterisk here, or that multiplier symbol, doesn't just mean multiplication, but it means multiplication by the complex conjugate. So in other words, the probability that a given in-particle system exists in a particular differential volume in the universe at a particular time is proportional to the wave function for that system multiplied by its multiplied by its complex conjugate, right? Okay. Now, an important thing is that postulate 2, this idea that the probability of the system being related or being proportional to that simple multiplication of the wave function times its complex conjugate is what gives the wave function its significance, right? It's what lets us say something about that quantum mechanical system existing in a particular way in the universe at a particular time. And because that system has to be somewhere in the universe, if it's real, right, and we care about it, right, we can normalize this probability in an important way. That'll come back again in a minute. Specifically, what we can do, what's typically done, is to say, well, the system has to exist. It's got to be somewhere. Maybe I don't know where, but what that means is if I integrate that expression, that multiplication of the complex conjugate by the wave function, or the wave function by its complex conjugate, right, d tau, and if I integrate that over all space and time, that's just going to be equal to 1, right? So that's an important sort of normalizing property of these wave functions. Now, this can be written another way, right? There's another type of notation you'll use, and I tend to use this when I write these things out because sort of the way it was taught to me. And that's something where this integral over here is written a different way. It's written with these angle brackets. And you put the wave function in here, right? Not writing this out very well today. And these angle brackets, this is sometimes called, for the physicist who came up with it, or mathematician, Dirac notation, right? And those angle brackets with the bar in the middle basically mean the same thing. It's sort of like multiplication of this wave function by its complex conjugate integrated over all space and time, right? Okay, and that equals 1. All right, so that's our second postulate. Our third postulate. Okay, postulate 3. This postulate is related to physical measurements or physical observables, the things we would care about, right? The idea that you've got a quantum mechanical system out there, and yeah, it's got to exist, but if I can't take a measurement on it as a experimentalist, biochemist, or biophysicist, yeah, I really maybe just don't care very much. Theorists, different matter, but experimentalists, we want to take a measurement, right? Okay, and postulate 3 says that every physical observable of a real system for example, right? Energy, right? Position, momentum, all of those kinds of things, right? Kinds of things we might want to know about, right? Is associated with a particular type of mathematical object, specifically is associated with a linear Hermitian operator. All right, this is a sort of statement of our third postulate, that all physical measurements we might care about are associated with linear Hermitian operators. Right now, there are several things in there. What's Hermitian, right? You guys may or may not remember this. If you look back, you've had some linear algebra, you might remember it. It's important, but it's not necessarily germane to this discussion at the level we're going to have it, except for one point that I'll make in a moment. Even more for some people, what's an operator, right? Where did that just kind of came out of nowhere, and that sort of freaks some people out when they start thinking about this stuff to begin with. One thing that's important to know is that operators get a certain notation. So operator notation looks like this. It gets a little hat symbol, right? So if I had some generic operator, right, that was associated with some physical measurement or property, and I'm just going to give it a generic, like a capital P, that operator would look like this. It'd be P with a hat on it, right? That means an operator, right? Now, second question, what's an operator, right? When you think about it, like what is an operator? And that may seem like weird nomenclature or terminology. You've never heard of it before, but you have heard of it before. You've just never heard of things called this before, potentially, right? So you guys know, this express, you know what this does, right? d dx, right? That takes the derivative of some function of x, right? That's a differential operator, or in formal terms, that's the so-called differential operator. Or how about this one? Sine. That's a sine operator. Or square root, right? It's a square root operator, right? And the list goes on and on and on. You've seen these like crazy. These are big mathematical operations that do something to a number or a function, right? Are operators. The term operator, as it's used in quantum mechanical operators, is just a slightly more abstract statement of this basic idea that you guys have all seen since you first started taking mathematics in high school, or even junior high school, right? Okay, so our third postulate is that all these physical observables are associated with a linear Hermitian operator. Okay, all right, it's postulate then number 4. All right, postulate 4 states that every classical quantity, think about it, what's quantity, physical quantity, has an associated quantum mechanical operator, right? Some examples, right? So the classical quantity we might be thinking about would be something like, position, for example. And that gets the symbol Q, as I've already shown you. So position, right? Or momentum, which you guys may remember, gets the symbol lowercase p. Or time, which is lowercase t, right? Or energy, right? Gets an uppercase E typically, right? Okay. That each of these has an associated quantum mechanical operator, and the quantum operator of course gets an associated symbol, which would be Q with a hat, right? Or P with a hat, lowercase p with a hat, or T with a hat, or E with a hat, right? There's an associated quantum mechanical operator. And these, of course, then have a particular form. The quantum mechanical operators have a form which looks like this. In the case of position, it's just a simple multiplication, right? Hey, the quantum mechanical operator is essentially equivalent to the classical quantity. It's just a straight multiplication. Its position in space is its position in space, right? A minimum operator, however, is a little more complicated, right? It looks like this. It's minus I, right? That's an imaginary, fundamental imaginary number of square root of -1 times h bar, and h bar is just Planck's constant h divided by 2 pi, right? Right. The quantum mechanical operator is -I times h bar times the partial derivative of some function of motion of an object with respect to position, right? So it's the partial derivative. Those are not very well written out, partial derivatives. Oh, I'm sloppy today. With respect to position, right? Okay, time, kind of like position, time is just time, so it's a straight multiplier, right? And then the energy operator also gets a somewhat special definition, and it's kind of not terribly different from momentum, right? It's -I times h bar, and a partial derivative, in this case, with respect to time, right? Okay, so that's our fourth postulate, all right? That all these classical quantities have an associated quantum mechanical operator, right? Okay, now, fifth postulate, right? We're almost there. Postulate 5. Now, what we really want to do with quantum mechanics, right, with this description of the wave function of a system, is we want to measure something, right? I've sort of been alluding that in my description of, the multiplication of the wave function by its complex conjugate is what gives something real meaning. It tells you the probability where that, or it's related to the probability a system exists in a particular differential volume. Talked about the fact that all physical measurements are associated with linear Hermitian operators, right? So postulate 5 sort of takes this one step further, an application of this operator to an actual physical measurement. And what it basically says is that the average value, right, of say, and let's go with that that generic, like, doesn't really associate with the operator, say P is capital P, right? It's not a real thing, but that operator, let's say it's linear or Hermitian, and is therefore associated with a real physical observable, a real physical quantity, something like energy or momentum, if you applied it to a wave function, right? What postulate 5 says is that the average value, if I took a lot of measurements, the average value that I would get from those measurements is equal to this quantity, which is basically the integral of that wave function complex conjugate multiplied by the application of that operator to the wave function, right? Or another way to say this is that application of the operator to the wave function, then multiplied by the complex conjugate, divided by sort of the normalized probability of that wave function, the system described by that wave function in space and time, right? And another way to write this using Dirac notation, it's a little simpler. Those bracket notation is what this is sometimes also called. Just looks like this: P right? So this is sort of the core of postulate 5, right? That the average value returned or represented by application of that operator P, right, is obtainable by application of that operator to the complex conjugate, to application of that operator to the wave function, multiplied by the complex conjugate, integrate space and time, normalize it, and we should like learn something, right? Now, depending upon the nature of that wave function, this can get really complicated in all kinds of different ways. And the interesting thing is that in many cases, and essentially all the cases we would care about in biochemistry and biophysics, probably except when you're really moving out into the periphery, the following turns out to be true, which is that if this is a physical observable we really care about, it has an interesting relationship with its wave function, right? And it looks like this. So in many cases, application of that operator to this wave function will, upon application of the wave function, application of the operator, return the operator, same form of the wave, application of the operator to the wave function, in many cases, will return the wave function in the same form, right? Multiplied by a number, right? So this is not what I've written here. This is not the momentum. This isn't momentum, right? This is just like supposed to be a lowercase. This is just a number, right? It's like a real number, right? So in some ways, this is kind of a corollary of postulate 5 for most of the cases that we would end up caring about. The fact that application of the operator returns a real number, right, is guaranteed by the fact that these operators that are associated with physical quantities are Hermitian, right? Means that this will always be true. Now, another little bit of nomenclature for operators and wave functions that do this, right? When this is true, that wave function is said to be an eigenfunction. So particular nomenclature, an eigenfunction of operator P, right? And that real number, that application of that operator to that wave function, if that wave function is an eigenfunction of that operator, that real number also gets a name. It's known as the eigenvalue, right? Of that eigenfunction when operated upon by that operator P. Okay. Now, one of the reasons these two things are so important, I keep referring to sort of real things, is that for physical observables that are associated with an operator like P, that return eigenvalues from systems that are eigenfunctions of that operator, when this relationship holds, right? What that means is that the physical measurement that is represented by application of that operator is going to return the same value on the system every time. The measurement is stable, right? Okay, there's going to be noise, which is why the sort of average value, right? But you're going to get the same basic number every time you take the measurement. If the wave function is not an eigenfunction of that operator P, right? Then different measurements will give different values, and it is not predictable when or how or why different measurements will give different values, right? Which is why for physical stuff we would do or care about, this is the kind of system that we would normally be worried about, right? It's going to essentially anything we care about will fall into this category, right? All right, final postulate. All right, postulate 6. Okay. For this to work, for all of this stuff that I just talked about to work, right? To be able to, like, you know, make these measurements and the probability. And when it starts to get real down here in postulate 5, we want to take a measurement, right? With, you know, applying some operator to learn something about this system. We want real numbers coming back, but for all of this to work, right? The fundamental thing is you need a wave function, right? If you don't have the wave function, none of that works. It all collapses, right? You got to be able to specify in all of this you must be able to specify the wave function. And that's the trick. How do you do that? Right? Okay, well, postulate 6 states that the great German physicist Erwin Schrödinger basically figured this out, right? That Schrödinger supplied the answer in what is known as the Schrödinger equation. And it basically says that if I were to apply the quantum mechanical energy operator, this guy right here, right? That partial derivative with respect to time. And I applied that to the wave function for some system I was interested in. H bar, right? If I were to apply this, right, to the wave function, so take the partial derivative of my wave function with respect to time, right? What Schrödinger showed, right, is that if that's true, right, but I can do that, right? What turns out to be true is that application of this other operator, which I'm going to give the symbol H bar, and I'll tell you in a minute, to the wave function, is going to have the same result, right? That those are going to be the same thing. Remember, we're talking about here, we're applying the quantum mechanical energy operator. That's what that represents, right? So application of that operator to the wave function should tell us something, or tell us the energy of the system, right? And what the Schrödinger said is that, well, there's another operation that should do the same thing. And that's the application of this other operator. It's known as the Hamiltonian. Right? In honor of a great Irish physicist by the name of Hamilton, who set about in the 19th century recasting classical Newtonian mechanics in terms of kinetic and potential energy, right? Specifically, this sum of kinetic plus the potential energy of a system was given in honor of Hamilton, a name. It's given the symbol H, right? Okay, well, if we, like we saw before, we have classical, this was done sort of for, classical mechanics. There's a associated quantum mechanical operator, right? And it turns out to have exactly the same form. There's certainly a quantum mechanical kinetic energy operator, right? There's a quantum mechanical potential energy operator. And that is where the Hamiltonian operator comes from, right? Remember, K is the symbol for kinetic energy. And V is the symbol for potential energy. Right? So what this says, let's say something about what it doesn't say. You might look at that and go, oh, well, that means therefore, what you've done this is that the Hamiltonian operator is equivalent to the quantum mechanical operator, right? That we just talked about, partial derivative time, right? That's wrong. That's not true. That's not what the Schrödinger equation says at all. So don't make that particular mistake. What it does say, however, is that the application of the Hamiltonian operator to a wave function will return the same value as the application of the quantum mechanical energy operator. This partial derivative with respect to time will return the same value as the Hamiltonian operator will. They're both going to return the same energy for a quantum mechanical system if we know the wave function and it fulfills postulate 5's criteria, right? Okay, that's pretty cool, all right? But this is still, everything I've said is a little abstract. So what does that look like, right? So let's think about that, right? Let's have an example of this. just to sort of whetting our appetite. What is a Hamiltonian operator? What does a Hamiltonian look like? And we're going to look at this for just a particle moving in vacuum, right? For a sort of a simple moving particle. Right? Not being operated on by any outside forces, just a simple, I misspelled that, didn't I? Look at that, that's great. Let's try that again. Okay. All right, well, we remember, or hopefully you remember from your high school physics, that the kinetic energy of a particle like this is simply equal to the momentum squared divided by 2 times the mass, right? Pretty simple, right? So assuming a Cartesian coordinate system, we can apply then the quantum mechanical momentum operator, right, to this system, right? And it would look something like this. So if we wanted to derive a quantum mechanical kinetic energy operator based upon something that is described classically this way, that quantum mechanical kinetic energy operator would look like this, K with a hat, right? Now we have to apply that operator, if you remember, right? I'll just write it over here again, just minus I h bar partial derivative with respect to coordinate, right? Okay. So that would look like this. So minus I h bar partial derivative with respect to x times this unit vector I. Now this case, the I is not the imaginary number. That's the unit vector in one of the 3 Cartesian coordinate directions, right? Maybe you guys remember this. Plus partial derivative with respect to y times the unit vector, oops, j, plus the partial derivative with respect to z times the unit vector k, right? All of that squared, right? Because we just applied the momentum operator, right, to a particle moving in Cartesian space, right? All right, so we got to square it, all right, divided by 2m. Okay, well, that's kind of ugly. There's some way we could simplify that. Seems like we could, right? One of the ways we can simplify that is by changing the notation a little bit. The way this is done is it would say, well, I can write this minus I h bar, and then this chunk of this, right? Those derivatives with respect to the spatial dimension gets a symbol, right? Gets a name too. It's also it's known as the gradient, right? But it gets a symbol, this upside down triangle with a thick top, right? It's known as a del, D-E-L-L, and it's also known, as I said, as the gradient, right? So it's the first derivative of something, some function, with respect to spatial coordinates, right? Okay, well, we got it. We're not done yet. We got to square that guy and then divide it by 2m. Okay, but okay, if you square the first derivative, that means you're really taking the second derivative, right? So you're applying that derivative twice, right? So we can write this we can rewrite this. This would technically look like this, right? Where we square the minus, and the minus square root of 1 turns into a minus 1, right? So we end up with minus h bar squared times partial derivative, second derivative partial, plus the second derivative, second partial derivative with respect to y, with respect to x, with respect to z, right? Divided by 2 times the mass. I should have mentioned, did I mention it? I don't remember if I did or not. The m here is the mass of our particle, right? So if that's momentum, m is mass. Okay. Okay. So all we did was basically, apply that squared term. Okay. So now we got second derivatives, right? The imaginary number went away. That's cool. So we can write this a slightly different way, which is now minus Planck's constant divided by 2 pi squared. And this second derivative with respect to spatial dimensions also gets another symbol. It gets that del symbol again. Having a hard time drawing it today. Squared divided by 2m, right? So just the del alone, as oh geez. That's, as I said, known as the gradient, that first derivative. The second derivative, del squared, is known as the Laplace operator. Right? Okay. So now putting these ideas together, if we wanted to write down the full Hamiltonian for our particle moving in space, right? That Hamiltonian would look like this. It would be h bar. It would equal minus Planck's constant divided by 2 pi squared times the Laplace operator divided by 2 times the mass. Pretty straightforward. But the full Hamiltonian, that now the particle's not under any outside influence. It's not moving through any sort of potentials. There's nothing else going on. That would be the end of it, right? But to be complete, since, maybe there is going to be an outside potential, we would have to add in the potential energy operator to get the full Hamiltonian for this particle moving in space, right? So we have the kinetic energy part, right? And the potential energy part here in our Hamiltonian. Okay, so the potential energy in the system is going to depend on the nature of the system, and it's usually going to also only depend upon operators of position and time for the kinds of system we're going to care about. And so this basic setup of what a Hamiltonian would look like is going to lead us straight into thinking about how light is absorbed by matter, right? Okay, and I'll give you a hint that all of the explanation for it in terms of the description we're going to go through ends up in this potential energy term of the Hamiltonian describing the absorption of light by matter. Okay, and we'll pick that up next time.